and a station for the new people as well. So, without further ado, everyone, are you ready to join us for the first session together? Are you ready? พร้อมไหมคะ If you are ready now, so please join me in welcoming Professor Pierre Piana, the President of WPO. ขอบคุณค่ะเรียนเชิญค่ะ
Very good afternoon to everyone. Henki, can you hear me there?
Yes.
So coming through clearly? Right. Nice to be here. We've got quite a full program. And I'm going to start off with doing glass. We'll do metals thereafter, and tomorrow we'll look at paperboard, and we will look at plastics. So I thought we'd start off with the more easier ones today and then ease ourselves into polymers tomorrow, which sometimes can be a little bit challenging. So let's just have a look at what constitutes the various types of packaging, but focusing in terms of, in this particular presentation, on glass. And this is a workshop, so I don't want to just stand up here all the time. Any questions at any stage, please ask. That's the only way we learn. So don't hesitate to ask me. So let's have a look at that first scene. When one looks at that photo, it installs something differently in every person. What I'm seeing in that photo and what some of you might be seeing in that photo is very different. For me, I look at the material. For some of you folk, you might look at the context. And when you see lollies or candy or sweets like one on the right, that is very different for a different age group. A young age group will immediately focus on that. When we look at the scene on the left-hand side, and having just come through COVID, we view that very differently. So you can see how our minds change with time. Because prior to the COVID vaccine, COVID-19, this image here would have been a very different image in your minds. Now all of a sudden, we're all very familiar with the vaccines, and so you're now looking at that with a different eye. And the material, maybe, you're looking to see whether that material is suitable for that product. And that's what I'm referring to here, in that our minds change all the time in terms of our understanding, appreciation, and value that we obtain from the material. You can remind me at any stage to stop immediately and ask me questions. So I'm hoping that this What about enabling portion packaging? And portion packaging, especially here in Thailand, is very big. There's a huge demand for portion packaging, or what they call unit dose packaging. One dose of sugar for your tea or your coffee or whatever it might be. It must communicate and inform. And on purpose, I've taken a very simple pack like bread, because you cannot get more simple than that. But yet, that packaging for that bread is ideal, and it keeps the cost down. And economics in packaging is something that we must always remember, always. Every decision we make in packaging relates to cost. Pricing, and I'm sure that in your workspace you all know that already. And so we cannot just simply choose a material. We cannot choose the cheapest material every time. It might not work to give you the shelf life that you require. can go up to 5 or 6 levels as well. But do you all understand what these levels are? So then we've got a product in glass, and so that bottle is the primary packaging. In other words, the product is coming into direct contact with the primary pack. The product is coming into direct contact with that packaging, makes it the primary packaging. So you've got to understand that. Whereas though, if I just go back one, the box on the left is the secondary packaging. And then that box might go into a corrugated shipper, and that becomes the tertiary. So you can see over here, we've got the different levels until you're ending up on a pallet. And a pallet goes into a container. So and all of a sudden you can see now that the different levels as we go up. All right, now let's have a look at some of the other areas. We looked at containment. What about compatibility? Remember I said that glass is inert. So we could in fact use glass for everything. But we don't because of price. Glass is more expensive than plastic. But certainly from a compatibility point of view, it'll be perfect. So now we've got to check whether that product can be used in a particular material. And when we talk plastics tomorrow, I'll explain to you the various types of plastics. And there's a range of different plastics. And how we make the choice in using the different plastics so that we don't make an error and you're faced with a problem in the market and you have to do a product recall. That is very expensive. Retention, and you can see here in the flowers, for example, that is being supported and is retained and restrained in that carton. And for those of you who have ever been involved in flowers, packaging, it's a very unique sector of packaging that not many people get involved in. Every single day, millions of flowers are moved across the world, predominantly in Europe, where the main flower market is. What about separation? And you can see in the images there on the bottom right-hand corner, you can see those bottles are being separated to prevent any damage to the bottles. What about cushioning? And you can see in the one with the pink foam, it's cushioning that high-end product. Especially when you get your optical items, they need a lot of cushioning. They also need clearance around that product to make sure that there's no banging of the product on the side walls of the carton, which could potentially be something on the outside that's hitting it and it breaks the bottle. And most of all, it must support. Now, these ones that are listed here doesn't mean that every product has every aspect there. I'm just mentioning them all to you so that you are aware of it when you're making your decisions. Positioning. Now you might think, well, what is positioning? If you look at the blue box at the top there, which is a large carton, and that's lifted up by a forklift. If your positioning of that heavy machinery in that pack is all on the one side, when you put the forklifts in and you lift it, it's going to fall over. And imagine damaging it. So you have to position it suitably in the packaging so that it remains stable when you're lifting on a forklift. These are things that you as a packaging person has to decide. You've got to be aware of it to check that you don't have an issue. Because it'd be really embarrassing if you design something and as soon as they lift it, it falls off the forklift. Non-abrasive, depending on the product, it mustn't damage the product. The weight distribution is similar to the positioning as I've explained. Suspension, you can see that in that, not working, but in the middle image there, its positioning is suspended in the center of that carton, so it cannot be damaged. What about visibility? Bottom right-hand corner. For many of us, we want to see what we are buying, and we won't buy it if we can't see it. So then what we do is so that the consumer doesn't open the pack, we then make it visible for us to see. And in that way, no one damages the packaging. Closure, well, obviously the entire pack must be closed properly, otherwise it's of no value, and it must have instructions on it. So in packaging, there's a lot of ingenuity required. And sometimes it's quite simple. If one looks at the matchbox, this image over here on the left-hand side, the matchbox has been around for a long time. But it's ingenious, it's never been changed. There's some modifications of it, but in principle, the matchbox has remained the matchbox all this time. Some of the other ones here, the one on the top right-hand side is a product called Locked for Kids, and a child cannot open that because they need both hands. And that dexterity only comes into a child at around about the age of 4 or 5. So a 3-year-old won't be able to access that blister pack, for example. And some of the other images here, on the bottom right-hand side, normal cans, they just change the packaging configuration. So you get this point of difference, which attracts the eye. The wine protection that's been designed there is very simple but unique and very effective. Once that bottle there is encased in that packaging, you can comfortably drop it from 1 meter and it won't break. We need to be creative when it comes to packaging as well. And what you see across this image is here, the different aspects of creativity from different people. Even the tissues in the bottom right-hand corner, it's sometimes very difficult to get the last tissues out of a box. But by having this, it ensures that you can push the inside up when you get to the last, say, 20 or 30 tissues, and you can then reach them quite easily. So ingenious, really, really creative. What about connecting with the consumer? We know that back on the left, by Heinz tomato sauce or ketchup. The one on the right is a brilliant invention, but so simple. Instead of having a sachet that often messes on your shirt or your blouse or your dress or your suit when you're trying to open a sachet, they have this back. And you can see how you squeeze it. And you can actually control the flow by squeezing your fingers. Brilliant pack, really, really good. So you're really connecting with the consumer there in that particular design. Again, if one just looks through these different images here, you can see how effectively the different designers have looked at connecting with the consumer. One of them is honey, for example. We all know the color of honey. No matter what country you are in the world, be you in Thailand or in Singapore or Philippines or wherever, you know what honey looks like. And you know what product you're looking for when you walk into a foreign grocery store, and that is connecting with the consumer even though you are not from that country. What about point of difference? You know, the Coke is a very good example of this. The Coke's a very big player in the market. We all know that. So when they found that their Coke sales were not on the increase and beginning to plateau, what they did was they brought out the Coke of that, or whatever country you're in, and they started putting names on it. And once we all like to see the name of someone we know. So when you see the name, all of a sudden you buy the Coke. You had no plan to buy the Coke, but because you knew the name of someone with that name, you bought it for that person. And so the sales on Coke went so well that so many countries joined in the same program across the world for Coke. And now we see it on so many other packaging types. What about potato chips, crisps? This is a rather old one, but I'm just re-emphasizing the point of difference, the eye-catchingness. In the left hand, we know that potato chips are normally a shiny material. So what they did on the right-hand side, they brought out a matte finish. And all of a sudden you had the point of difference. All the other potato chips on the shelves were shiny, excepting the ones that were matte. And so your eye was attracted to that pack and you purchased it. The same with this wine, this particular bottle. It's normally round and they brought out a square bottle just to be different. And so you get eye-catching point of difference. What about cost-effective packaging? In other words, over-packaging. And you can clearly see all these images here potentially are over-packaging to some extent. We can have a long debate on the bananas and the strawberries, I understand, but certainly the one on the left over here, I think you'll all agree that for that type of product in that pack, you do not require all that protection. What about the guidelines for effective packaging? And we always try to keep the barrier, the highest barrier, closest to the product. Remember that, the highest barrier closest to the product. So if you're looking at those layers there, the highest barrier there will be aluminium. So aluminium must be as close as possible to the inside of that Tetra Pak. That's effective packaging. What about looking at the design of cartons where there's over-engineering? And we see this fairly often in corrugated packaging. And I'll emphasize that more tomorrow in relation to designing it suitably for that particular product that you're using so you don't overuse the board. Likewise with the image on the right-hand side. If you're using high volumes and that lamination film there is maybe 70, 80 microns, if you went down to 70 micron, you still maintain the shelf life, that's important, but that saving of 10 microns over a few million packs can be of value to your company. This is when we are replacing something by a new material. Be very careful when you simply just replace, because it's cheaper. The top one was glass and they moved it to plastic. They're the same with the milk, in a rigid container to flexible. So you've got to be really careful. Even with the advent of all these stand-up pouches, you also need to ensure that you are considering the effectiveness of that pack in all manners, not only the material type, but how well is it accepted by the consumer. As I've shown you a few slides ago, how easily is it to open and close and to handle. So this slide that you see here is probably one of the more important aspects that all of you should remember. The correlation between the Tetra Pak and the shipping container. Why I've done that is so that you can understand that when they designed this Tetra Pak, back in the late 1980s, early 80s, sorry, when they designed Tetra Pak, they had to make it 1 litre. Why did they make it that shape? Anyone know? They made it that shape because they changed the primary packaging to maximize space efficiency in the container, in the shipping container. So when you pack Tetra Pak into a shipping container, you get around in the 90s, anything from 92% to 96% in space efficiency in a container. And that's what you want to achieve. That previous slide I showed you, that really poor efficiency rating, that rating was in about 65, 68%. So you're wasting 30% plus every time regarding the space utilization. So I re-emphasize, if you remember nothing so far, remember this slide. The one in the top right-hand corner, those tins there, when those are 5 different 5 different products from 5 different companies, and all those tins were different sizes by a few millimeters. What we did was we got those 5 companies together, and we came up with a size for the container that was suitable for all those companies. And in that way, we could reduce the price, because you are producing so many more tins that are all of the same size. And at the same time, we ensured that the containerization of those tins was maximally done. All right, For those of you who attended this morning in the conference, we looked at this image because when we design packing, we want to go for the optimum pack design. What do I mean by that? We don't want to overpack and we don't want to underpack, because when we underpack, we could waste food because the packaging is not suitable. If we overpack, we could waste a lot of packaging material. So we've got to find that spot, the optimum pack design point, so that we don't overpack and we don't underpack, but we maintain the suitable shelf life for that particular product. And that will vary from every product that you're packing. So you can't use one outcome for any other product. You've got to evaluate every single product to ensure that you obtain the optimum pack design. Okay, you won't worry about that. I was looking at how does one have a look at the one of the latest trends across the globe. I want to touch on this one because this is so important. The slide of the containerization is the first important aspect I've discussed this afternoon. The second important aspect is this permeation theory. Now, some of you might not know the permeation theory or Fick's law, but I use the balloon as an example, because if you blow a balloon up for a party and the next day you come to the balloon's gone flat, it's deflated. Where has the air gone? The air has not gone through the knot that you tied in the balloon. The air has gone through the layer of that material. It's permeated through the wall of the balloon. So we take the same principle into packaging, same principle. And that's how we determine shelf life. And every one of you that are involved in packaging should, if not must, understand the theory of permeation. Because ultimately we look at the water vapor transmission rate and the oxygen transmission rate. Those are our two pivotal points that we always look at in packaging. We've got to understand water vapor and oxygen to understand the shelf life of a product. So we're going to look at diffusion, Fick's law, this afternoon. So I'm explaining the balloon concept to you, and I'll now take that into a packaging environment. So the horizontal line at the top and the horizontal line at the bottom, I've increased the thickness of the material of the balloon. I've just made it big so you can see what's happening. The other aspect that we must think about is this RAM, relative atomic mass. Now, don't worry about too much about those words that if you haven't done organic chemistry, you might not understand. Just look at the principle and try and understand the principle. In the relative atomic mass of hydrogen, it has a relative atomic mass of 1. Carbon, 12, nitrogen, 14, oxygen, 16, and chlorine, 35. And that relative atomic mass equates to the size of that molecule for that particular element. Okay, for those of you who remember the periodic table at school or at university, that's where those things come from. But for you folk now, all you have to worry about is taking those different elements and equating it to a size, because relative atomic mass shows you the size of the molecule. And it's those molecules that try and force their way through from a high concentration or a high pressure inside the balloon, the pressure is higher, to a low pressure or a low concentration. That's what those molecules are doing. They're going from a high concentration or pressure to a low. So you can see the top is high pressure, the bottom one's low pressure. Listen very carefully, the two ladies in the front, because you'll have to explain this to us afterwards. Make sure you remember what I'm telling you. So, over a 24-hour period, and you can see down below here, we measured in grams per square meter over 24 hours at a particular temperature and a particular relative humidity. and we have a look at how much of those molecules are coming through in 24 hours. You've got to remember that that image there is in a plain two-dimensional scenario. You've got to imagine it as a three-dimension, because those A's, which are atoms, are moving all the time. In this chair, in this floor, in the ceiling, in that concrete, they're atoms, they move all the time. Believe me, they're moving. You can't see it, but they are moving all the time. Same as in a material, in the balloon, it's moving. So if one looks at the black and the orange, you can see the molecules trying to come through, but it's blocked. At that moment, it's blocked by the atom. The very next moment, 1 second later, there could have been a slight movement and it could slip through. So those molecules are trying to get through, and we measure how many of those come through the wall of the balloon in 24 hours at a particular temperature and a particular humidity. And that is how we determine the shelf life. Shelf life is determined by that theory. So you've got to understand the theory to determine shelf life. And you've got to understand the theory to determine which material is the best material for your product at the cheapest price. Don't forget, you've got to remember the cheapest price, always. Okay, and that's just showing you how we apply it. Right, now that we've looked at the basics, and I'm sure and I'm hoping that all of you understand them. Any questions before we go into glass? Any questions from the two ladies in the front that you'd like to ask? Is Ms. Atala listening? Any questions from you? Not. Right. Any questions from anyone else? Okay. All right. So don't forget what we've done so far in the last 20 minutes, because we're now, bearing that in mind, that what we've done, we're now looking at glass to see if glass is going to be the most suitable packaging material for what we want to use it for. Right, let's have a look. You can see the variation of glass there, all different shapes and sizes. This are plates and vases. It's very different to bottles for beverage and pharmaceutical. And they're all different types of glass. We don't use the same glass for all the different end uses. Remember that? Different glass. What is glass made up of? Silica sand. Silica sand is the main constituent of glass. And you can see there, it's 60 to 75%. Now, some countries do not have silica sand, so they can't manufacture glass. Mr. Wabawe, do you have silica sand in your country, in Indonesia? All right. Is there anyone in this room that does not have silica sand in their country? Because if you don't have it, you cannot manufacture glass. And then you have to import it. You can't import sand. Imagine importing sand on a ship. It'll be hugely expensive. Soda ash, 12 to 18%, limestone around 10%, and cullet. Cullet. Anyone know what cullet is? Cullet? You know what cullet is? What's cullet?
The recycled glass.
Exactly, well done. Cullet is recycled glass. And we can use up to 20% of cullet in glass. 20%. And we want the cullet in glass. We want it. Why? Because it runs the furnaces very hot. It helps with keeping the temperature up when we're melting glass. What temperature do we melt glass at? Any idea? How much? 700. Mr. Wabawe, what temperature for glass? To melt. There you are, 1,200, 1,400. That's a very high temperature. I'll show you in a moment. All right, that's cullet. And what is cullet? It's about, normally that's the size that they crush the cullet to, about 20 millimeters. You think I'm not going to ask you any more questions, that's why you're leaving. Is that right, Mr. Atta? Okay. All right, so we use cullet to make sure the furnaces keep that high temperature because it burns nice and hot. All right, I've just shown you a snapshot. There's so many different glass items, so many. I've just given you a short idea of the different glass, because in a moment now I'm going to show you the different types of glass. So you can see there foods, non-foods, pharmaceuticals, even things like closures like the glass stopper. You don't see them very often, but they're still around today, the glass stopper. We have type 3, type 2, and type 1. Type 1 is the most expensive. We use that in pharmaceutical. It's got borosilicate glass, and we only use it where we really have to. And then the cheapest one is type 3 glass, and as you can see, that's general glassware. Okay, I'll show you this image because ultimately I need you to have a vision in your mind of what we're trying to make. And we all know a bottle. And that's a very standard bottle. But the bottle has a lot of important parts to it. Because you must understand the parts, you understand glass manufacturing. Why do we need to know the parts of glass manufacturing? Simply because when we are designing that bottle, we've got to get the flow of the glass suitable so it flows nice and evenly all over that bottle. And I'll show you in a moment some images where those aspects have gone wrong. And if we don't understand where we require the flow to be suitable and we use the right name when you are corresponding with the supplier, then you won't get the message across in what you're trying to achieve for your particular pack. Okay. So those are the 5 steps that we look at very briefly. We've got the raw material, we put it in the furnace, we melt it, we then put it through the molding process, anneal, and then we quality check it. Let's go through those more definitively. That's the furnace. And we heard a moment ago there, 1400 degrees is not unusual for the melting of glass. 1400. So it's really, really, really hot. This photograph, for example, you can imagine, this is a guy here, you can imagine how hot that must be to be able to work so close to that particular furnace. When one looks at this gives a nice image of what we're trying to do in the glass. You can see all the components being added into the furnace. You can see the furnace there. That's then transferred into your mold. Now remember this image for those of you who are coming back tomorrow for plastics. Because what we do in plastics is very different what we do in glass. Glass is very aggressive. We need thick molding apparatus. These parts over here are they're ceramic based, very different to what we'll see tomorrow in plastics. But they're still mold, all right? So bear that in mind tomorrow when we mold. That's when the bottle is just coming out of that molding process. So that temperature there, you can imagine, is extremely hot. You cannot get close to that. Even with protective garments on, it's a challenge to remain there for an entire shift. And so they change the shifts quite regularly in terms of people working close to the furnace. What I always say to people is, if you like your holidays, don't work for a glass manufacturing company, because glass never stops. Because if the glass solidifies in the pipes, you can imagine you've got a problem. All right, so glass never stops production. All right, we've got 3 different types of ways that we mold glass. The first one is blow. All right, so really what we're doing is we've got the gob coming into the mold, and you can see the mold then closes, and we force air into it, first phase, and then we blow in the second phase. You can see it then folds it up. All right, so we call it blow. And when we blow glass, we only blow when the orifice, remember I'm now using terminology because I showed you that bottle, the orifice of a bottle, which is this over here, when the orifice is smaller than the diameter of the bottle, then you have to blow, right? If we go to the next one, and we go press blow. Yeah, we're pressing the mold first, that's the gob of glass, G-O-B, gob. You can see the mold closes, we have a male die coming in and we make that shape for the first phase. That's the press part. When we blow, you can see we transfer it, close the mold, and we blow it up into the jar. Again, we have to blow because that size is smaller than the diameter of the bottle or the jar. All right, so we press blow, and then the last one is press. And here it's that first phase only, like a glass for drinking water or something like that. So those are the three different ways that we manufacture glass. All right, now, when that bottle comes out the furnace, yeah, it's just come out the furnace. As it comes out the furnace, we put it into an annealing oven. Annealing oven. Why do I emphasize that word? Because this is what it looks like. That's the oven. As you can see, it's a massive long oven, but it's a conveyor in there, but it's temperature controlled. So as it comes out the mold, it goes straight into the annealing oven. What happens in the annealing oven is this, In the annealing oven, we raise the temperature of those bottles going in. We hold the temperature there for a period, and then we slowly bring it down. And this then relieves the stress in the bottle. So in a way, it's sort of realigning the molecular structure. So by reducing that stress, if we hit two bottles together, they won't break. If it has not been annealed, if you hit two bottles together, it will shatter. So every bottle that you see around in this show, every single one would have gone through an annealing oven. How do I know that? Because it would never have reached the show. It would have broken long ago. So that's why I know that every bottle in the show has been through an annealing oven, which is that oven there. All right? So we realign the molecules in that structure to relieve the stresses. All right. Now, unfortunately, we have defects in glass. We'd like everything to run perfectly, but it doesn't. So then what we have is this one. We have seeds in the bottle. They're little air pockets that form in the bottles. Not really common, but they are there. It does happen from time to time. We also have bubbles, which are large ones, large seeds. All right? We then also have stones. So now you might say to me, well, why do we have stones? You told me that you melted the sand, silica sand. Well, you know what? If I've got silica sand out there in the land, and I'm collecting the sand, we know that the wind blows. So some grains of another sand, not silica sand, might blow into the silica sand. So now you have a foreign grain of sand. And that foreign grain is not silica sand, so it's not melting at 1400. It could melt at 2000. Well, we're not going up to 2000, we're only going up to 1400. Therefore, that stone has not melted. That's why it's there. All right? It's a natural product. Glass is natural, sand. Yeah, we've got a spike. It's an accumulation of glass. So we have two problems here. When you have a spike, that spike could dislodge. If it dislodges, it could end up in your stomach. And then we have a problem. And you have a problem as well, because you've got glass inside you now. The other problem is when we have a spike or we have a bird swing, wherever we have glass, I'll come back to that one, or that one. No, okay, yeah. You can see here we've got these marks in there, but I want to show you. Here we've got more glass lying at the base of the bottle. Now, that is one problem in case it breaks loose there. The other problem is that when we've got glass accumulating here, remember you had a gob amount of glass that went into the mold. But if there's a whole lot here, it means that these walls are now thinner because you're taking glass away from the walls and it's lying at the bottom. So it becomes a major problem because the walls of the container are that much weaker. And when you have vertical pressure, it could break. If you stack the glass bottles 10 high on pallets, imagine the bottom bottle. It's got a lot of vertical pressure on it. So potentially it could break. All right, let's just go back to Whoopsie. Where am I? Okay, so we've got bird swing. Now, when you saw the way that we manufactured the bottle, you saw the different processes. So you'd think there'd never be a bird swing. Well, guess what? There's a bird swing. I've seen 3 bird swings in my life, and I've been in this industry 37 years. So I know they're bird swings. But they shouldn't have happened, but they do. And when you fill the bottle, that liquid coming down into the bottle could break this filament of glass. And now you've got a filament in the bottle, and when you drink the product, you've got glass in your stomach once again. So it's a big problem. So we want to be really careful. And the bottle manufacturers around the world are really, they watch the quality aspect of glass so closely. Every single bottle is photographed, right, and relayed to a reference bottle, a perfect one. And when there's one that's not perfect, it's rejected. So that's how they control this sort of thing. These are just flow lines that are in the bottle because of the natural sand. This is very important in high-speed filling, because when that nozzle comes down into the bottle on filling, it cannot hit the sides. So the bore of that orifice is exact. And that's how you can now control it, because if it hits something, it's going to shatter that bottle. And you can imagine a shattered bottle in a high-speed production environment. That is a mess, and the line has to stop. And remember that these are running at about 11, 12 bottles per second. It's about 38,000 per shift. So there's a lot of wasted money as soon as a high-speed line comes to a standstill. False bottom, the same story there. And there you've got the one I spoke about, fused glass. All right, so there are many benefits of glass, and you can read as well as I can read there. But it is a very environmentally friendly material. It is inert. It is widely accepted in the food industry and the pharmaceutical industry. But it is more expensive than plastic. So that's why we've got to make that decision. Remember, right up front, I told you, we're making a decision about the economics. Because ideally, we'd like to go glass on everything, because it's inert. It looks good. But the product might not be able to support the price. Okay, just showing you some of the advantages, and then some of the disadvantages. And you can see the top one and the bottom one are the ones that come to your mind first, and quite rightly so. Okay, so we'll take a 5-minute break before we get into the metal side. Are there any questions on glass? Yes, sir.
Do you have an NNPB process? NNPB.
Yeah.
Can you explain how it works or how
NPD?
NNPB.
NNPD.
NNPB. Is that narrow neck press and blow
That might be another presentation.
in the class?
Yeah. NNP.
Because you have blow and blow. What about NNPB?
What are those acronyms standing for?
I think it's narrow neck press and blow.
Because those are the only 3 that they use. Okay, what we're discussing here is the different forms of glass. Remember the blow, press, blow, and straight press. Those are 3 different types. Now, what could be the case in this particular question is in some countries, the naming of those international way of naming it might be different in some of your countries. But there are only 3 ways of making glass. You know, even if you take a small vial or a small ampule, we still have to use one of those processes. I just used a simple example of a bottle and a glass jar and a drinking glass, because that explains it so much easier to the listener. But in an ampule, for example, we would still have to do a blow, because you've got a very small orifice and you've got a slightly wider body. So just so that you know, But if you take this terminology back to whatever country you are, I presume that most of you are in Thailand, but I know that in some cases there are some different naming of those different forming systems. So that might be what you're referring to. Any other questions? Okay. Have you been listening?
Yes, and like a balloon, because it's so interesting because it permeates the gas, the air permeates the wall of the balloon and leaves it. So even though there is a knot, the barrier, that the wall doesn't have a barrier to gas, so it permeates and leaves.
You can do work and listen. as they walk past, and that's normal in these sort of shows. So, but we'll continue. Thank you for those that are here. We're now going to look at metal. It won't take long, probably about half an hour max, but it'll give you a very good overview of metals, which forms an important aspect of packaging. It's the different uses of material for different packaging. Each is unique. One is not better than the other. There's a particular space for metals, same as there's a particular space for glass. You with me? You with me, you two gentlemen? Particular space for each one. So you can't say, well, glass is better than metals. Not at all. Two different classes, we don't make comparisons like that. The only time we make comparison is if we are using glass, we might say, well, it's very expensive. Could I use plastic? Well, we'll talk about that tomorrow at 3 o'clock. Plastics tomorrow at 3 o'clock. At 2 o'clock, I'm doing paper and board. So any of you are using paper and board in your company, we're going to look at paper and board tomorrow. All right. So you can see here, there's a huge variety of different metals. You've got steel cans, you've got tin plate, you've got steel on the aerosol, you've got aluminium on the cold drinks, you've got tin plate up there. Here we have also tin plate, and over here we have aluminium foil. I will touch on metallization as well, because there is an amount of metal, that's why it's called metallization, but I will touch on that towards the end of this lecture. All right, let's have a look at looking at tin plate or aluminium, because they are the most common ones we use. Yes, we do use steel drums, but I'm talking about the normal person in the street. They often the common ones is tin plate or aluminium. And as you can see in the images at the bottom right-hand side, you've got the tin plate can, and you have an aluminium can, right? When you put them together like that, you can see they are very different, very different. The one can is hermetically sealed. The other one is a completely different process of manufacturing it out of a flat metal plate that you are pounding away in an environment that what they call double-walled iron. I won't go into too much detail, but it's a very different process to make an aluminium can as it is for a tin plate can. Those are just showing you the different types of metals that we are using in the steel section. And then I must remind you that when we are creating a tin can, like we use for vegetables, for example, that is common in the food industry, then we have to, and I'm going to show you the process in a moment, but be aware that is when we form that plate at the back, you want to join the two sectors together. And how do we do that? We do it by putting different compounds in there to ensure that you get a proper hermetic seal. So this one actually shows you how we bring those two sides together. Let's just go back one slide here. This is what I'm referring to, this join down the back of a tin plate can. How do we do that? This is how we do it. We can either mechanical clinch it, which is this image at the bottom there, where you're actually folding the one into the other. We can resistance weld, and we can seam it with putting an adhesive bond and joining it by normal adhesive. When I say normal adhesive, particular adhesive for the metal industry. Remember, adhesives are very particular as you get, the end uses are all different depending on what you're trying to bond. So don't bear that in mind. I just want to show you more closely what that forming of the body with the lid or with the base. And you're actually clinching it like that, and you can see that if this is the lid part, this is the body part, you can see the body has two sections and the lid or the base has in fact three. So when you're working out how much metal you're using, that's the formulation at the bottom. And that's very important. If you're looking at the economics of it, then this becomes very valid, especially when you're doing a lot of cans. So remember that. So as you can see, when we're making a can, like your Coke can, Mrs. Atla, you know you collect cans, Coke cans. This is how they're manufactured, so pay attention. Right, you can see over here you've got a roll of that tin plate. You can see we cut it into sections, and then we stamp out the size of that body. So we stamp out the size of the body. We roll the body, and then we want to clinch that, like I've just explained, and close it off there. And then we put a base onto it, and we send it to the filling processing company. They put the contents in, and they put the lid on top, and then mechanically clinch it again. So if I go back, they've got to go back to this mechanical clinching when the end processing company actual fact folds it. So bear that in mind. That's of a simple tin can. Now your variation could, in terms of the thickness, as you're getting bigger cans, so the thickness proportionally increases, so that it can take that added weight of it, but not very much. We're only talking a number of microns, not millimeters. Don't worry too much about this. In terms of tin-free steel, these are, again, depending on what the product is, depends on what type of metal structure we can use. Because remember, if you have a high acidic, you then have to put a coating inside that tin can, like a varnish, so that there's no interaction. That's why, going back to the last lecture, we'd rather have glass, because glass is inert. If you have tin plate, then or tin-free steel, you could have a reaction, especially if it's highly acidic. If it was aluminium, different story, because if it's aluminium, then we wouldn't have a reaction. That's the next closest to glass in terms of inertness, but it's not fully inert, but it is better. But the problem with aluminium, why don't we use aluminium for all our metal uses, is simply back to economics. It's too expensive. So therefore we go to tin-free steel or tin plate, but we've got to make sure that we have to use varnishes or internal lacquers if we want to ensure that we don't have any interaction. Okay. Right, let's have a look at manufacturing process of foil. Because foil we use in the manufacturing when we do laminations. And when you folk come back next year, and we look, tomorrow, I'm going to be explaining flexible material. And in there, I'll show you how we laminate materials together. And we could be laminating foil, a layer of foil, which is different to metallization. Don't mix the two up. They both are aluminium, but very different processes. So how do we make a roll of aluminium? So if you use aluminium in the kitchen at home, that's the principle of making that foil or manufacturing into sheets is exactly the same as the foil that we would use in a multi-laminate material structure. Same process. So what happens, aluminium is a mined product. So once we've done the refining of that, we end up with an ingot or a shape, whatever shape that might be, a block of aluminium. And if any of you have ever made pasta, and you're rolling pasta, it's exactly the same process, only in a very industrialized way. So we have a block of aluminium, and we roll it, and slowly we're getting it bigger and bigger and bigger and bigger, and flatter and thinner and thinner. And then we cut it to the size and roll it up, and we end up with a roll of aluminium. That's how you make aluminium. It's very rudimentary, although the processing of that has been refined so much in recent years in this process of actually rolling it. But the principle compared to pasta is exactly the same. You know yourself, when you roll pasta, you start off with a thick layer of pasta, and when you finish, it's a nice thin layer that you then slice up. Same here. We roll it thin and we slice it up. Exactly the same. Okay. Now I want to explain to you metallization, because metallization is a very different process to aluminium. The only correlation between this and what I've just explained over here is I will take that aluminium, 99.9% aluminium, and you all know these products, these chocolate products, and you love chocolate, so you've seen it before. And when you open the chocolate, it looks like there's aluminium inside there. But that aluminium is not the same as the aluminium that's in your kitchen. The aluminium is the same, the way of making it's different. All right, so when we make a product that is used ultimately on Cadbury's Crunchy, and when you open the Crunchy, it's got a nice silver look to it. The way we do that is you take 99% pure aluminium. Listen carefully, because when you finish, you'll be able to explain this to someone else. When you boil a kettle, Mrs. Pellegrino, you're listening carefully. When you boil a kettle and you put the spout against a mirror and you boil it, what happens to the steam coming out?
No idea. No idea.
Yes, you do know. The vapor out the spout settles on the mirror and forms droplets. You know that. Yeah. And those droplets is exactly the same principle we use in metallization. All right? We take the aluminium, only difference here, we don't have it next to a mirror, we have it in a vacuum chamber. So we heat the aluminium up and it vaporizes, and then when it condenses, same as the water on the mirror, droplets, when it condenses, we let that settle on a moving belt of some or other polymer film, polypropylene or something like that. And it settles on there, and it ultimately, it looks like the whole thing is aluminium, but it's not. You want a layer of plastic there, and these droplets of vaporized aluminium. Very, very thin. It's like 40 angstroms. It's very thin. If you looked at that under a microscope, you'd see what, Alexa? You would see droplets. In other words, there's spaces between the drops. But to the human eye, it looks like it's all covered. It's not. So it's not 100% barrier. Don't be misled that metallization is 100% barrier. It's not. If you use aluminium foil, like for example I explained over here, that gives you 100% depending on the thickness. If it's too thin, like about 17 micron and less, you could have pinholes in that. In metallization, you definitely have lots of pinholes. So when you look at this under a microscope, it's little droplets, like water on a mirror. It's aluminium on polypropylene or some other substrate. So you understand the difference. So this all happens in a vacuum chamber. Moves, and the melt is continually moving, and the vaporizer of the aluminium settles on it, and you wind it up, and it looks like it's all aluminium, but it's not. Okay? But there's a need for it, there's a use for it, and you can see yourself, and you've eaten Crunchy before, and many other products. Next time you open one of these packs and you see nice aluminium on the inside, you know that that is metallization. And you can explain to someone what metallization is. So you can see there the advantages of aluminium. It's light, it's soft, it looks good, it's shiny, it attracts the image, no rusting. The only problem is, number one, you can't solder it in cans, and number two, it's expensive. So we cannot use aluminium for everything. That's why we have tin-free steel and tin plate and steel and all those other metals, because we can't use aluminium every time. Economics always plays a part in packaging. All right, and then I'm just finishing off with aluminium, just to show you that's the aluminium you use in the kitchen, and all of you know that. And this aluminium here is around about the 15 micron mark. So potentially, if you look through a microscope, there will be pinholes. There will be pinholes. All right, you just can't see them with a naked eye. So you look as though it's a nice, beautiful film of aluminium, but there are holes in it. And that's why when you have a blister, if you have a blister pack, and you all know what I'm referring to on a blister pack, the ones where you pop out the tablets, you know, Mrs. Pellegrino, the blister pack there, all right? This one, you got aluminium on the one side, rod on the other side, and this here would be around the 20 micron mark, aluminium, no pinholes. Because if there were pinholes here, remember what I told you about an hour ago about permeation? The moisture will permeate through the holes and your tablets will go soft and it won't have a shelf life. Ms. Atla, you understand? Okay, so we go thicker. But in the kitchen, you don't have to have it thicker. It'll be too expensive. So we go 15 micron, about 15 micron. Could be a bit less, could be a bit more. But just to let you know, there is a difference there. All right, and then round up and sell it, and perfect, bingo, we got the answer. Thank you very much. Are there any questions? I can see on your face. Do you have any questions? Are you sure? Alexa, any questions? Okay. Nothing. All right. Mr. Cameraman, you okay? No questions? Can you explain metallization to me? You can. I won't ask you, but you can, eh? All right, you can explain it tonight to someone, if you had to. If someone asks you what's metallization, you'll be able to sort of explain. You know? Would you, Alexa? You could? There you go. Exactly. But I won't embarrass anyone. But as long as you now know that next time you see a crunchy, that's metallization and not aluminium foil. Good, thanks very much. The next lecture is only starting at 3:30, I think. Right, so you got a bit of a break. Thanks very much.
แป๊บนึงครับโอเคครับ
Thank you very much for your information right here. Thank you so much. Please give a big round of applause for our special speakers today. All right, so ladies and gentlemen, just now the speakers is Professor Pierre Pienaar. He is the president of WPO right here today, and he is a very famous speaker from another country in Thailand. This is a great honor to welcome him to right here to be the speaker for all of you for today's event. All right, now I would like to welcome everyone to the innovative stage right here, and we have many topics that we would like to show you what we have today. And let's see, for the next session, we'll start at about 3:30 p.m. And for the speakers for that session is Soha Atala, the Vice President for Conference, Exhibitions and World Star, or the World Packaging Organization, WPO, with the topic of post-COVID packaging trends. So anyone, if you want to join us for the topics of post-COVID packaging trends, so you can come here at 3:30 p.m. All right. And for the next session, for the third session, we would like to show you for the topics about sustainability in packaging by Luciana Pellegrino, Senior Vice President for Marketing World Packaging Organization. And after that, at the fourth session, around 4:30 p.m., so we have Q&A session. Anyone, if you want to ask any hesitate or if you have any more question about the topics, about all the topics today, our special guest or the special speakers, Professor Pierre Pienaar, will come back right here again for the Q&A session. So everyone can join us together right here. All right, see you for the next session at 3 p.m. So thank you very much to Professor Pierre Pienaar for informative and useful information. All right, see you for the next session at 3 p.m. with the topics that's very interesting topics today over here at 98 Royal Hall 98. Okay, come back again and make appointments with us 3:30 p.m. with post-COVID packaging trends topic. Thank you. See you. ขอบคุณค่ะ